You're fine. I should probably state the monotone convergence theorem at the start, and I should probably write it in super tiny font up at the top here so I can leave it there. So here we go. I'm going to make the monotone convergence theorem. I'll put it up here. What does the monotone convergence theorem say? It says that if Fn is sequence of integrable functions that is monotone almost everywhere. Almost everywhere, and the absolute value of the integral of Fn is less than or equal to m for some constant m. For some constant m and all n in the natural numbers, then there exists integrable function f such that Fn goes to f and, in norm, my bad. It's easy enough to miss that in norm. In norm and Fn goes to f almost everywhere. Moreover, the absolute value of the integral of that function is less than or equal to m as well. All right, so this is the famed monotone convergence theorem. All right. And I think I stated the Lebesgue-dominated convergence theorem as well last time, didn't I? I think I ended with that. So this was 2.83. The Lebesgue-dominated convergence theorem was well, again, I think I stated this I think I wrote this out last time, right? If a sequence of integrable functions Fn converges almost everywhere to a function f, and there exists an integrable function h such that the absolute value of Fn is less than or equal to h for every n and n, then f is integrable, and Fn goes to f in norm. That was that one. I think the next thing for me to state was Fatau's lemma. So here it is. Theorem 2.8.5. Fatau's lemma. It says let f n be sequence of non-negative integrable functions such that the integral of Fn is less than or equal to m for some m, and each n and n. All right, if Fn goes to f almost everywhere, then f is integrable. And the integral of f is less than or equal to m. And as he mentions, this is due to Louis Fatou. I'm probably mispronouncing that. Fatou. Anyway, 1878 to 1929. Oh, I've missed the first two names. Pierre Joseph Louis Fatou. Well, I have two names when you can have four, right? And let's see here. So I feel so inadequate. I've only got three. But let's see here. But the proof is by the monotone convergence theorem, and it's about 2 paragraphs here. But I'm eager to get to the next section, so I'm going to move on. Well, I just wanted to state these and kind of just look at them for a second and just try to get it in our system, because as we look at proofs in like the future sections, they use these, especially the monotone convergence theorem from what I saw reading ahead a bit. So what's it say? If f is a sequence of integrable functions such that it's monotone almost everywhere. In other words, it's either strictly increasing or strictly decreasing everywhere, right? Almost everywhere. And the absolute value of the integral is bounded for each term in the sequence. Then there exists an integrable function that the sequence converges to in norm and almost everywhere. And then moreover, that function has an integral which is also bounded by m. So, okay, and let's see, in difference, what about this lemma here? What's this give us? We've got a sequence of non-negative integrable functions. The integrals are bounded. Notice the difference between monotone convergence and Fatou. See the data? Oh, so nothing, I don't see monotone anywhere here, right? Just non-negative integrable functions, right? See that? Nothing about monotone here, just non-negative integrable functions, such that, and it doesn't have absolute value, right? He's got just straight up the integrals bounded by m. Of course it's non-negative, so you could add absolute value there. Like, you could wrap this in absolute values, I think, reasonably, because it's non-negative, right? So like it's equal to its absolute value anyway, but there's no cancellation that can happen in this thing. And but then it's an implication though. If we have a convergence almost everywhere to f, then f is integrable and the integral is less than or equal to m. So these are genuinely different animals, right? But all right, so I'm going to erase this as board spaces at a premium today. And I want to start the next section right there, so. All right. Are we okay, Audric?
Yeah, we're good.
Okay. Okay, so this brings us to section 2.9, which is on locally integrable functions. So. And you might say, what does that mean? Well, let me tell you. So here we go. So here's the definition. The integral of f over AB is denoted integral from a to b of f, all right, and is, let me just say that that's equal to, what's it equal to? It's equal to the Lebesgue integral of f times the characteristic function of ab. Hey, look, he's finally using the characteristic function notation. Ah, it's about time. So he's been, I feel like in writing this book, they were fighting, no, we're not going to use that notation, and then finally got to this section, and they're like, dang it, we need an explicit notation for characteristic function. I guess we'll just have to put it in. He's managed to dodge this notation in so many places by using words. but denotes the characteristic function. Which, remember, means what? Chi AB of t equals to what? 1. Yeah, exactly. 1 if t's in there, and 0 if else, right? All right, and this is just the ordinary product, like pointwise defined product of functions. Go for it.
When we last kind of first introduced characteristic functions, we were talking about them on half-open intervals.
Oh, yeah, but
Since it's closed, does that if it's the right interval, if it's B, would the characteristic
well,
function be?
I mean, I suppose to be fussy, it's not a step function.
Yeah. Well, right. Oh, yeah.
According to our definition, but nevertheless, that is a using the half the Clopen intervals is it is a choice that's made in this book for the formalism, but it is not a necessary choice. Like you could work with opposed. You could work with like open on one side, closed on the other. And his next paragraph, basically, he's like, you know, the choice of the closed interval AB in the definition has no significance. We could use the open interval AB or the semi-open intervals, and we'd have a completely equivalent definition. And he says, in the proofs, it's more convenient to use exactly what you're saying. In proofs, he says, he'll probably replace this with chi of, you know, A, B like that for convenience in proofs, you know. Although I'm not sure I remember seeing that yet in my reading, but I'm sure it's in there somewhere. All right, so let's talk about a theorem here. So this is, I think I mentioned this, guys, in brief before, but like, so to define the integral over, you know, like the definite integral, we just basically just make everything 0 everywhere else, but you'd still do the Lebesgue integral, it's just mostly 0, you know? Okay, so theorem. This is theorem 2.92, 2.9.2. It says if f is Lebesgue integrable, so L1R, then the integral from a to b of f exists, you know, for all intervals. Let's see if I can go through the proof of this. All right, so what's it look like, proof? So we're given f is represented by f1 plus f2 plus ... right? Because it's Lebesgue integrable. And then he says define for n equals to 1, 2, and so forth, gn of x, right? And it's going to be equal to fn of x for x an element of AB and 0 else, right? And then he says, you can see, evidently, you know, I think gn of x is equal to fn, is equal to f of x times the characteristic function of AB, is that right? Well, that's not what he says. That's not what he says. He says, that's not quite right, what I wrote. I need to start bringing a snack. I'm low energy at this time of day. It's not a good time of day to be low energy. So he says it's easy to check. F times the characteristic function of AB is that this function is represented by the series of G1 plus G2. Dot, 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 dot. Let's see, is that true? What does it take for that to be true? Didn't we have, if they're equal almost everywhere, that was sufficient?
Well, the little mark there, the equivalent thing is the sum. So F is the sum of all of them multiplying them right by the characteristic function. And based on how G would be defined, would just be equal to G1 plus G2 dot dot dot. And so since it would be equal, I guess we just write it from this maybe? No, sir. That may be wrong.
I'm trying, just a second here, let me take a walk down memory lane for just a minute.
I think it's just kind of like a
Oh!
like literally GN has to be, or SI has to be represented by the G's.
But didn't we, but what did, my question is more basic. What do we mean by that symbol represent there? Do we understand it? Oh, look, what I'm referring to here, guys, is corollary 2.711 on page 58, where we learned that F is represented by F1 plus F2 dot dot dot. Then, oh, that's not if and only if, though. That's then. That's if then.
Well, in the definition on page 45, F is that means we write that with the sum
45, let's see here.
at the bottom of the definition. So in that case, it would just be like what Audrey was saying. It quite literally would just be that representation by multiplying through by the characteristic function.
So they're,
Because that is the sum of all those.
so that, all right, so first of all, you need the condition that the integral, the sum of the integral's absolute values is less than infinity. Condition A on page 45, and then condition B is that that point-wise the sums match, right? Like, yeah. Man,
But we know it already matches all those conditions because F is in one of our.
Oh, right. So we know that, we also know, okay, so we know that F times chi AB is the product of an integrable function with a step function, which I think we know already that is
Yeah.
once more integrable. Okay, so like, yeah, condition, what I'm trying to say is condition A we don't need to worry about. Condition B, I think what was Audric was saying about like 3 minutes ago. Sorry about that, Audric. So if
Oh, you're fine. Yeah.
if I put in X here, I get, well, is that equal to, question mark, G1 of X plus G2 of X plus dot 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 dot? I mean, well, there are two cases, right? if X is not in, so if X is not an element of AB, then F chi AB of X is equal to F of X chi AB of X, which is, of course, then equal to F of X times 0, also known as 0. But by construction, G1 of, likewise G, right. So, and of course, Gn of X is equal to 0 for all n as well. So in that case, it works, right? And then the other case is it's in AB, right? In the other case, if it's in AB, then we have f chi ab of x is equal to, well, f of x times 1, right? But that's equal to f1 of x plus f2 of x plus dot 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 dot, because f is represented by the sum of the f's, right? And those are literally equal to gn of x on such x. So which of course is equal to g of x. Well, I'm defining that to be g, I guess, but anyway, the point is that this paired with the observation you already made out, A is already satisfied. F chi AB, man, my voice is going today, is G1 plus G2, okay. Great, so long story short, if we have Lebesgue integrable, then we have integral, the integral on AV exists, right? Conversely, what's that?
I like integral for Lebesgue integral.
The converse is easily dismissed, though, right? What? No. This is my conservative vector fields from physics are still in my mind. Conversely, if you look at the integral from a to b of, like, you know, the constant function 1, right? That exists. But 1 is not an element of L1R, right? So there definitely are functions which are locally integrable in this sense. Well, excuse me, that there are functions for which the integral of, I should be careful, we're about to technically define locally integrable, let me not misuse the word. So there are functions for which this integral from a to b exists even for arbitrary ab, right? I mean, you know what it would be b minus a. This would be equal to b minus a if we went through it. But 1 is not a Lebesgue integrable function, right? Because if you integrate 1 over the whole real line, you know, that diverges for sure. Okay, so that is why we introduce yet another definition, which I will do now.
Oh man, now we can't say integral.
Don't worry, you'll get over it. Let's see here. And, oh, I shouldn't have done that. I've got no juice. I'm out of the juice, and I was throwing my marker, my cleaning bottle in physics. I needed a projectile, it's the closest thing, you know? So I had to throw it, but then I forgot it's on the floor. And here it goes, definition. A function on R is locally integrable. Locally integrable. If the integral from a to b, f, exists for every minus infinity, less than a, less than b, less than infinity. So basically for any finite, you know, if the integral exists for any finite, for any closed interval, right? If the integral exists for every closed interval, then it's said to be locally integrable. So the constant function 1 is locally integrable, right? Even though it's not integrable. So
We're saying the constant function diverges because when you eat it off, it basically goes to infinity.
right, because if
The definition of Lebesgue integral.
yeah, I mean, because right. So if the Lebesgue integral is basic. The Lebesgue integral is in some sense a formalization of the integral from minus infinity to infinity, in the Riemann sense. So, you know, if you have, you know, if your function doesn't go to 0 eventually, then you're out of luck. But yeah, if we sort through the, you know, the step function, like what's a you know, a series of step functions that represents 1 would be.
That represents 1, but just, I mean,
Characteristic function.
I don't know.
See,
1 over 2 to the f.
it's just, I mean, you could just do like the sum n equals 1 to an, well, oh gosh, I don't know. Well, anyway, that.
So, I mean, are you talking about something that produced the 1, or?
I'm asking, since you raised the issue, I'm trying to think about how I would actually calculate the integral, how I would attempt to calculate the integral from 1, the integral of 1 in the Lebesgue sense. Like, how would that be defined? I think it wouldn't be.
Well, yeah, no, the series itself, like if you have 1s, then it would diverge. Oh, no, that's not what you're saying.
I mean,
No, I mean, like you said earlier, Jacob, on page 40, the first condition is that the sum of the norms.
Oh, I
The sum of
see.
the integral of the norms, it has to be less than infinity. So,
Yeah.
like, it fails the first condition.
Yeah. Yeah.
I mean, but I suppose technically I would have to show that there doesn't exist a sequence of functions that, you know, how do you show there doesn't exist a sequence of functions that represents 1 subject to conditions A and B, you know?
Oh, because that we're saying 1 is f.
If you're saying it's,
So, oh, you're saying, oh, wait.
I'm sure that this falls under the,
Are we saying that 1 is this constant sequence for it, or are we saying that 1? Oh, we're saying 1 is.
I'm saying f of x is identical, f of
We can have
this function.
a sequence of functions that represents 1. I can have just don't think it's Lebesgue integrable.
Oh, yes. Well, yeah, I'm not saying you can't represent 1 with a sequence of step functions. Sure. I granted. I mean, I think you can be very silly, right? You can just kind of like this step function, right? Then this step function, you know, and then this step function, and then this step function, and then that's what I was trying to think of the formula for that, you know?
Yeah.
So like you could just take steps from one integer to the next, and you'd have all numbers covered. You know, golly, what is that thing? I mean, that's like, I don't know. I can't think of the formula for the stupid thing.
Oh,
But it's the characteristic function from
it's the linear combination of characteristic functions.
and n plus 1, right? And then
Yeah, they define it.
and then you just take union over n in the integers, yeah? That's equal to f.
Yeah. When you construct a function, yes.
But I don't know if that,
Then
anyway.
are we restricting what we mean for the definition then? Of the individual function?
Are we what? I'm sorry.
Are we then just restricting what we mean by locally integrable function? It's like the function's not defined on the whole line, but if you take this subset, then you're fine.
Well, locally integrable it's a function with domain R, such that the integral over in any, you know, the integral from a to b for any choice of any finite pair a less than b, you know, that integral exists. So that makes sense for functions which are not Lebesgue integrable, as exhibited by this. This is not Lebesgue integrable. I'm not sure how to prove that to you at the moment, but I'm trying to figure out a simple. I think there's any number of theorems that probably would strike that down. Yeah.
I mean, I don't think you had to prove it to us. I mean, it's just failed the first condition.
Does it? Because you'd have to show that there does not exist a sequence of step functions.
Yeah, I was getting confused. 1 is f itself. It's not the constant sequence of terms of the 1, 1, 1.
I mean,
Yeah, so
I agree that it's true, but to show it directly from the definition, I would have to show that there does not exist a sequence of step functions that satisfies those two conditions. But, well,
Well, I don't see, okay, so, the definite interval of 1 can't be, like, how to be equal to the sum of the integrals of step functions.
I mean,
I fail to see how that's possible. Because that's how you define it. You define it by the sum amount to n to infinity of the step function, of the integral of the step functions. So that means you'd have to have a convergence set of step functions, you know, like that doesn't really make sense.
Yeah, no, that does make sense. Based on the definition of how the integral of a step function is,
Like,
41. Page 41.
like let's say fn does converge to f, like, but you're taking the integrals of each particular fn, and then you're summing them.
mm-hmm.
I don't see how that gets you back an indefinite integral of 1 for any constant.
Yeah, okay. Yeah, and it's also, it's for every x and r that condition, the second condition has to be the case. And so if we go outside of, if a and b are, or if a is 0 and b is outside of, is, greater than 1 kind of thing, and based on the integral, the definition 2.2.1 on page 41, Audrey's right, condition 1 of the Lemaitre integral function would fail because the integral would be greater than 1 because you have, the characteristic function serving as the weights of the different the lengths of the intervals would be greater than 1, I think, if I'm saying that right. And so then summing all that up, you would get something, a series with terms bigger than 1.
Well, I think, yeah, I mean, maybe. But I mean, I think you guys are right. I think you could just assume that you had an arbitrary step function. Like suppose you had a sequence of step functions that, that represent f, right? Then I think, I feel like you could argue that the series has to diverge everywhere by the like the nth term test or something like that. Something dumb like that. Listen, I'm going to go on because I don't think I think we are chasing an uninteresting rabbit at the moment. And where was I? So let me move on here. Okay, so locally this theorem then, in terms of locally integrable, what does it say? Theorem 2.92, we can reformulate to say what? Integrable implies locally integrable, right? But this example that we're quibbling over shows you that locally integrable does not imply integrable, right? So.
You said integrable implies locally?
Yep, that's what this theorem says right here.
Yep.
So, okay, and he says, although in the definition we require integrability over every bounded interval, it suffices to check the integral from minus n to n exists for every n, and that's one of your exercises. So, all right, so moving along here, Theorem 2.94. Let f and g be locally integrable. Locally integrable functions if G is bounded on AB for every minus infinity less than A less than B less than infinity, then the product FG is locally integrable function. Now in your homework, there's an example, exercise 39. It's like 1 over the square root. They play a game with 1 over the square root and show that you can have a product of locally integrable functions that is nevertheless not locally integrable. But it doesn't have this bounded property. So so it must be the example that they're talking about. The well, anyway, let me not do the homework. Okay, so let's focus on this one here. Focus, focus, focus here. So here's the proof. Let F and G be as in the theorem. And minus infinity less than A less than B less than infinity. All right, let big F equal to F times the characteristic function AB, and big G be G times the characteristic function AB. All right, there we go. Right? So we know that the integral from, we know that those are Lebesgue integrable, right? By definition of local integrable, I think. You know? So, but anyway.
I thought you were just saying that if it's integrable, last locally integrable doesn't imply integrable.
That's true, but to say that the integral from A to B exists everywhere is to say that F times the characteristic function is Lebesgue integrable.
Oh.
So it's just, yeah.
Okay. Yeah.
So, okay, he says let F, so he defined that. Now he's like, oh, okay. Now he's gonna, since as I just described, F is Lebesgue integral, you can represent it by a sum of step functions, right? Right? And he uses a word we haven't used in a little bit. He says they're step functions with supports. Support of Fn, a subset of A to B. Yeah, and my bad, I have missed it. I missed it. He puts, here's where he's doing his, like that there. All right. And he says we're going to show that FG is represented by, we can show F times big G is represented by F1G plus F2G plus dot 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 dot. Where G is not you know, G is the function that was bounded, that was given, all right? All right, so now we're going to use the bound for G, all right? So he's like, if G is less than M on A to B, then the integral of the absolute value of f and g is less than m times the integral of the absolute value of fn. Does that step make sense? I mean, so here we're using the properties of the Lebesgue integral. Well, okay, that's fine. I was like debating whether or not the integral of the absolute value of fn makes sense, but of course it does. It's one of the, you know, one of the functions that we're, one of the step functions we're adding together to, you know, give me f. I was debating whether or not that should be integral from a to b instead of just like the unadorned integral there, but I think it's fine. I think it's fine. So then what? Well then, if we look at the sum, n equals 1 to infinity of the integral of the absolute value of fn times g, that's less than m times the sum n equals 1 to infinity of the integral of the absolute value of fn, right? But we assumed, what did we assume here?
Oh, but that, since it's locally integrable, the integral from a to b of f exists.
Right. From this right here, right? So that's less than what?
Well, it's convergence.
Yeah, I mean this has to be less than infinity, right? Because this right here is the, going back to the definition of the Lebesgue integral, again, that series has to converge. And m times a convergent thing is still convergent in that sense, so there you go. Then what? He says, moreover, if, so that's the one thing. That's condition A of the definition. Now condition B, I think, we're working on. If n equals 1 to infinity of the absolute value of g of x, fn of x is less than infinity for some x in R, then what? Then he says that either the sum n equals 1 to infinity of the absolute value of fn of x is less than infinity, or so you notice here, this is pretty easy to think about because g has no n dependence, right? So like in terms of the calculation, it's the absolute value of the product of the absolute values. So you could just pull the absolute value of g of x out here. So if you think about that, for this to be, so one way this could be zero, be less than infinity, is if this is identically zero. So the one case would be g of x is equal to 0, fine. The other case would be that this is less than infinity, in which case that would be absolute value of g of x, whatever that is, times that, you know? So it's either this is less than infinity or g of x is identically equal to 0. I mean, it's equal to 0 for this x. So he says, in either case, the product of f of x times g of x is equal to, you know, in either case we have f of x times g of x is equal to some n equals 1 to infinity fn of x times g of x for that x. So let's see, maybe retrace our steps. If f and g are locally integrable functions, meaning that this integral exists for all choices of a and b, right? And g is bounded on a, b for every possible closed interval, then the product fg is locally integrable. So for it to be locally integrable means that we have to show that this integral exists for all ab. And how do you calculate the integral of that? Well, you have to take fg times the characteristic function of ab, right, and show that that's Lebesgue integrable, right? So that's kind of what he does here. Big F times, you notice that big F times big G is literally something that may be lost in translation here. Big F times big G is fg times the characteristic of function of ab. You notice that you don't square the the characteristic function times itself is, it's like, you know, 1 times 1 or 0 times 0. It's, so you can rewrite this. So proving that f times g is Lebesgue integrable, big F times big G is Lebesgue integrable, is tantamount to proving the local integrability of fg. And I think that's what we've done here. So it is interesting. You only need that g is bounded. You don't need that f is bounded. Isn't that funny? But if you look at exercise 39, you'll see that that example uses both of the functions you're multiplying to have the same secret bad sauce that ends up giving you the divergence. It's the old how do you create the 1 over x formula from, it's like 1 over square root and 1 over square root. When you multiply those, you get 1 over x. And then if you integrate 1 over x over the whole real line, yeah, it's something like that. I mean, I think it may be a little bit more nuanced than that, but that's essentially it. So let me go on here, if I can. Yes. So theorem 2.95. See, if I don't get to the theorem where we use monotone convergence, I'm going to feel really stupid about writing this out here at the start. Like, I know I need this. Well, yeah, only if you get to it, you dummy. Let's see here. So 2.95, it says this: if f is locally integrable function such that the absolute value of f is less than or equal to g for some g which is Lebesgue integrable, then f is Lebesgue integrable. Oh, okay. Well, that seems nice. Yeah. So that's a kind of a, you know, an upgrade to. Well, they're different, but they're kind of related, 2.94 and 2.95, right? Like here, we're assuming g is Lebesgue integrable. And it's bounding. It is serving to bound the f, right? So.
Okay, I think, okay. He says that if g, I'm sorry, I'm going back to theorem 2.9, sorry to backtrack.
2.9. 9.4 or 9.5?
Yeah, 9.4.
Okay, phew. Yeah.
He says in that, he says no if G is less than M on A to B.
Mm-hmm.
Actually, I think you need absolute value there for on G.
Well, M is positive here. That's assumed.
Yeah, M is positive, but I still think you need that absolute value sign on G. Like the absolute value of that function.
Does it need it?
Because if you go through that inequality, and you look at, and I'm looking at lemma 2.23 on page 42 also. That doesn't quite work out because you get an absolute value of G, and you set G strictly less than M, not the absolute value of G strictly less than M. Like I worked out that inequality, and I'm like, I don't know if that's right because it doesn't say that the absolute. It doesn't say M is greater than the absolute value of G.
Oh, okay.
Like when you get that the Fn times G,
Well,
absolute Fn times G.
but
If you work that out, that G doesn't disappear. That G doesn't pop out.
so you're saying we need absolute value of G less than M?
Yeah, and I'm quoting page 40.
But I think that's. But I think that follows from G being less than M, and here's why. So if G is positive, right?
Mm-hmm.
Then absolute value of G equals to G less than M. If G is negative, then the absolute value of G is equal to minus G, right? And notice that minus G is less than.
Equal to minus G?
What's that? Yeah, let me see here.
The absolute value is equal to minus G?
I'm in the middle of it. Just a second here. So I have. You may be right, Audric. G is less than M. I'm trying to do something doing here. So that's what we have. Can I do anything?
G is less than, negative G is less than.
Yeah. I wanted to do like this, Audric, but I don't think I can. You know, I don't think that's true. That's definitely not true.
Well, we have G is less than.
That's not true.
Oh, yeah, okay.
That's not true. So the thing is, I don't know. I don't know if it's like G less than minus G less than M, or if it's G less than M less than minus G with this given data. So, yeah, I think it would be right. Yeah, I think you're right, Audric. We should say this, right?
Yeah.
If we do that, then we're good, right?
Yeah, then
No.
it follows. But I was thinking about that inequality. I was like,
That's what bounded really should mean anyway. You want to bound, when you say something's bounded, it's bounded above and below, right?
Yeah.
So it's equivalent to supposing that. Well,
it's absolutely.
cool.
Okay.
Good.
Thank you for pointing that out.
Yeah, but I guess he's just assuming that from bounded, right? Then, like you said.
Yeah.
Okay.
But it's not what he writes. It's not what he writes though. You're right. So
Yes. So sorry for backtracking there.
no, it's fine. It's all good. So here's Theorem 2.95, and the proof uses that comment. It's like let Fn equal to f times the characteristic function on minus n to n. All right. N equals 1, 2, 3, so forth. All right. So if it's locally integrable, it means that, as he mentioned, that it's sufficient to check that this integral exists for every n. So local integrability implies that local integrability implies that the integral from minus n to n of f exists for all n, which is to say that the integral of f chi minus n to n exists, right? So this means that. And then he's like, say, let Fn be that, all right? It's like then F1, F2, da 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 are integrable. They're integrable functions. And Fn converges to, well, not Fn. Well, he says the sequence Fn converges to F everywhere. Is that clear? I guess that's clear. Everywhere, and the absolute value of Fn is less than or equal to G. Wouldn't you know? The one I needed for the one we got to at the moment is the Lebesgue, the Lebesgue dominated convergence theorem. See, because, all right, so here, locally integrable gives you that these, the Lebesgue integral of those exist, right? Then the limit to this, in fact, he says everywhere. In fact, almost, so everywhere implies almost everywhere, all right? So you have this sequence of Lebesgue integrable functions which converges to F almost everywhere. And you know that the absolute value of F is bounded by G, where G is Lebesgue integrable. Then by the Lebesgue dominated convergence theorem, this implies that F is an element of L1. So that's, again, by the Lebesgue dominated convergence theorem, which was in section 2.8, which I stated without proof, I think. Where'd it gone to? Page 60. All right. Oh, yeah, there it is. So there's a sequence of integrable functions converges almost everywhere to a function f, and there exists an integrable function h such that the absolute value of fn is less than or equal to h for every n, then f is integrable, and fn converges to f in norm. So we're using the integrable part. We haven't bothered with the in norm part, but there it is. All right, so that's, so 2.94 and 2.95 are kind of like nice, you know, as we've discussed, locally integrable and integrable, they're not equivalent, but there is some interplay, right? Like there is some interplay. And then finally, he mentions that this is the last thing he says, basically. Integral from a to b of f should be also minus the integral from b to a of f, right? So this is for like a greater than b. You define it to be that, all right? And also, the integral from a to a is defined to be 0, all right? So that's basically it. And he says that the subspace L1 of R, the subspace of Lebesgue integrable functions which are vanishing outside some interval AB is a vector space. And so like the vector space is, let me erase all this here. So L1 of AB is vector space. And what he means by that is these are, as he says, they're all functions that are vanishing outside some interval AB. So the support of these functions is contained in AB, right? Basically, that's the definition. F is an element of L1 AB implies that the support